Imagine you have a research paper all ready to submit, but then you remember that you need to have, for some reason, everybody's signature in pen ink. So now you have to visit your groupmates' houses as well as your advisors just to get their signatures on the paper. You want to do this quickly and efficiently because the deadline is approaching. Let's say the next day your sister brings you to a movie set that she for some reason was given access to as her designated photographer. She wants to have pictures all over the large fantasy set, so you have to go through every road. You don't have all day, so ideally you don't go down the same path twice. In this strangely specific scenario, we encounter two certain concepts in graph theory, namely the Eulerian and Hamiltonian paths, which is what we will discuss today. First, let us define some terms in graph theory. The formal definition of a graph is that it is an ordered pair G equals VE, consisting of a non-empty set V, called the vertices, and a set E, called the edges, of two element subsets of V. It would look something like this. Now, since we aren't computers, that is quite difficult to visualize, so we draw a representation of these sets, wherein the vertices become dots and the edges become lines. Now, a vertex V in a graph has something called a degree, and its degree is equal to the number of edges attached to it. And a graph can be either connected or disconnected. A graph is connected if there is a way from any vertex on the graph to any other vertex on the graph. And a graph is disconnected if there is at least one vertex on the graph that cannot be reached from any other vertex. Given a graph such as this one, an Euler path is a path that crosses each edge of the graph exactly once. A graph must have at most two odd degree vertices to have an Eulerian path. Note that if this edge is removed, the graph is split into two separate parts. The connected graph changes into a disconnected graph. An edge such as this is called a cut edge or a bridge. This edge is an important part of the Fleury's algorithm, which allows us to find an Eulerian path in a given graph. In performing the Fleury's algorithm, we begin at any vertex. We then go down any edge, given that it is not a cut edge, and this is the only choice you have. We then add that edge to our circuit path and delete it from the graph. We repeat this process until we cover all edges. In completing the Fleury's algorithm, we have our finished Eulerian path. Again, an Eulerian path is a path that crosses each edge of the graph exactly once. A Hamiltonian path, on the other hand, is a path that visits every vertex once, with no repeats. The difference between a path and a circuit is that a circuit must end right back where it started, whereas a path can be open-ended. An Eulerian circuit, then, is an Eulerian path that ends at the starting vertex. And a Hamiltonian circuit, then, is a Hamiltonian path that ends at the starting vertex. Now that we know the basics, let us move on to a more complicated graph, known as the weighted graph. A weighted graph's edges have numerical values called weights, which have an effect only on the Hamiltonian circuit. This is because Eulerian circuits focus more on finding the existence of such a circuit. The weights don't really matter because either way, you will go through every path. However, Hamiltonian circuits have something called an optimal route. Since you don't have to go through every single path, one Hamiltonian circuit may have less weight than the other, and the one with the least weight is considered most optimal. This can otherwise be referred to as the lowest cost Hamiltonian circuit. In this video, we will be discussing 3 certain algorithms to finding such Hamiltonian circuits. The first one we will discuss is the nearest neighbor algorithm. This is a simple algorithm. We begin anywhere and go down the edge with the smallest weight repeatedly until a Hamiltonian circuit is formed. This is considered a greedy algorithm since it is only concerned with immediate costs. It does not concern itself with how its immediate decisions affect its future options. In this case, the cheap option we chose forced us to take the most expensive route afterwards. The second algorithm we will discuss is the repeated nearest neighbor algorithm. This is, as its name suggests, a repetition of the nearest neighbor algorithm beginning at all the different vertices, after which the circuit with the smallest weight is retained. The repeated nearest neighbor algorithm is still a greedy algorithm. It is the nearest neighbor algorithm after all, just repeated, but it provides a better result than just the nearest neighbor algorithm alone. This is because it minimizes the effect of the starting vertex on the resulting weight of the Hamiltonian circuit. The third and final algorithm we will be discussing is the sorted edges algorithm. Here, we begin with an edge, but not just any random edge. We begin with the edge with the smallest weight. We then keep adding the lightest edges to the circuit, unless doing so gives a vertex degree 3, or it will create a circuit that is not Hamiltonian. We do this repeatedly until a Hamiltonian circuit is formed. While this algorithm is more apt to produce an optimal circuit than, let's say, the nearest neighbor algorithm, it is still a heuristic algorithm. It does not guarantee that it will definitely give the best optimum result. Going back to our weirdly specific examples, the scenic route where you take pictures of your sister is an example of an Eulerian circuit. Other applications include the line drawing minigame, where you don't lift the pen from the paper, road surface marking, and the Google Street View feature. Having to get everyone's signature in pen ink is an example of a Hamiltonian circuit. And other applications of the Hamiltonian circuit include vacation and tour planning, as well as bus routes. That is all we are going to cover in this video. I hope you enjoyed. Thanks for watching.